começar agora, né? Porque vai ter que agora. É 2 minutos.
Já estamos transmitindo para o YouTube.
Já passou perto de você.
Quem? Sim. Pois é, aí eu não gosto que alguém vá perturbar, aí bater na porta assim, eu desconfiei que era ela. E quem foi que bateu lá na minha porta? Quem está dormindo? Está em tudo.
Let me. Oh yeah, yeah. Can you hear me?
Hi. Can you hear me?
Oh yes, I can. Yeah, yes, yes.
Yeah. We are waiting.
Great.
No problem with the connection. Okay.
I think in general it's fine. I'm in UFPB now. I hope everything should be fine next hour or so. Just let me see if I can share my screen with you.
Okay.
So this is a presentation.
The icon share on the bottom.
Yeah, I know. Oh, my computer is so slow for some reason.
First, you start your presentation, and then you share it using this button, this green button.
Yeah, my computer somehow getting very, very slow. Can I just restart my computer? I will rejoin the meeting and then try again. All right.
Sorry?
My computer somehow getting really, really slow. So I need to restart my computer and then rejoin the meeting and then do the testing.
Okay.
Is that okay?
We are waiting the Weber, teacher Weber. I will call him.
Okay. Yeah.
We can wait here. The connection is okay. We are transmitting.
Yeah.
This is a conference over the internet using the YouTube. Okay?
Yeah. Yeah, fine.
Okay.
Let me see. So can you see my screen now?
Yunqing has started screen sharing.
Yeah, the screen sharing.
Not yet. Not yet.
This is screen sharing. This is a presentation I'm going to be showing. Yeah. Okay. It's quite slow. Let me
I think it's because your computer is a little bit slow.
Yeah. I'm just trying to do it now. I restart computer to see what happened. Okay, I will come back in 2 minutes. Let me restart computer.
Okay.
Somehow it's really low. I don't know what happened.
Are you using PowerPoint?
Yeah, I'm going to be using PowerPoint.
You can swap in the presentation because we have two screens. The presentation itself and the second window could be this the problem. Alô? Estou gastando meu inglês aqui, viu? Diga Weber que pode vir que a gente já está no. Não tá. We are rating.
Yeah. So
Perfect.
no, it's better. It's better. Let me try again if I can share my screen.
Your screen.
Yeah, let me see. Yeah, this one.
Okay. Okay.
Now, yeah, now it should
Okay.
be.
Okay.
Yeah.
Okay.
Yeah.
Valeu. And
Let me see if can.
Ere is already here.
All right. Hello.
Hi, Dr. Xuan. How are you? Nice to meet you.
I'm
glad.
fine. You all right? Yeah.
Yeah, good.
I'm just testing this. Yeah. This.
It's
So
okay.
is this presentation okay? I mean, can you see it? This PPT.
We are seeing you. Yeah. We are seeing
Yeah.
you and the presentation as well.
Only see me.
Yeah.
You can't see this presentation. Can you see the presentation?
Yes. Yeah. Yeah. We are seeing you and the presentation.
Okay. Okay. That's great. That's great. That's all I want to make sure. Yeah. All right. So yeah, I think that should be okay.
Yeah. All right. So we wanted you to be here, right? But we thanks a lot for you accepting this invitation for this kind of conference by video conference.
Yeah, that's easier, I think. Thank you very much. I'd rather to go there, but my agenda really limited. I have to go tomorrow morning. So yeah, the kind of only this afternoon I'm available. So again, yeah, doesn't matter. So I think that's the best choice. We can do it. Yeah, we can do it.
So I work with remote sensing.
Yeah.
And Professor Jonathan here works with hydrology.
All right. Okay.
We are really
Hi. Nice to meet you. Yeah, I see you.
A pleasure.
We are really interested in your presentation because we have data from the radar, which we have. It's a Doppler S-band radar here in NATO. And we are going to start using it this year with one of my master students.
Okay.
And she's calibrate this data and do whatever I want to do with the data to make sure if it's good. And Jonathan is planning to use this kind of data in some hydrological model.
Yeah. Okay. Yeah, that's very interesting to hear. Yes, we have been using this weather radar for quite a long time. I will cover that bit. I have seen your students, some of your students, the day before here in.
Amanda, yeah, Amanda is the one who is going to work with this radar.
Okay. Yeah. So yeah, I briefly had a talk with them. I hope they will find something useful here in my presentation. And also, I'm looking forward.
They just appeared right now. Yeah, they just entered the room right now.
Okay.
That's Amanda, yeah.
So looking forward to a future, any collaboration. Yeah, so that'd be good. So let's see.
That's gonna be great. So we're gonna start in about 15 minutes, right?
Yeah. Yeah.
You'll be free to leave the room and come back in 15 minutes.
Okay. Yeah. Sure. Okay. Yeah. I will come back.
The camera and everything you just set up right now.
Yeah. Yeah. I just leave it here. Yeah. Have a drink, some water. Yeah. All right.
Okay.
See you later.
See you.
Porque se altera a capacidade, Essa vida momentânea, né?
Ainda bem. Dr. Xuan, I'm just going to do a little bidding forecast here first, then.
Okay, yeah, yeah. And then I will try to share my screen with you all after I speak a little bit, then we start the presentation. Yeah.
Oh, okay, just a little bit. Verdade, essa vai ser uma palestra de 5 seminários um pouco não usual, né? 3, 4, 5 foram a João Pessoa quarta-feira, tá? Para a palestra do Dr. Xuan, e ele ficaram muito interessados na palestra dele, inclusive ele se constitui vir aqui hoje para fazer essa palestra para nós aqui no PPGCC, né? Para estreitar os laços da Universidade Federal, o trabalho científico que ele desenvolve conosco aqui. Porém, aí como foi em cima da hora, a gente não conseguiu trazer ele pessoalmente, então ele está via videoconferência, tá bom? O Dr. Xuan, ele é professor associado na Universidade de Xuan, no Reino Unido. Ele tem mais de 15 anos de experiência em desenvolvimento de estudo de hidrologia e também funcionamento remoto acoplado à hidrologia. Então, essa palestra dele vai tratar um pouco sobre modelagem hidrológica e associação com estimativa quantitativa da precipitação para input nos modelos hidrológicos, tá bom? Dr. Xuan?
Yes.
So, in advance, I would like to thank you for not to come because you couldn't, but
yeah.
We made some efforts to have you here via video conference. So thanks so much for
it's much better. Yeah.
The afternoon. So here we have a crowd of students and professors. We have master's students, PhD students, undergrad students. So everyone here is really interested on watching and seeing what you're going to present to us this afternoon.
Okay.
So feel free to start your presentation, and thanks so much.
Okay, no problem. So good afternoon, everybody.
Hi.
Hi. First of all, I would like to thank Dr. Weber and the group in your university invited me to give you a talk. Unfortunately, due to my very limited agenda, I can't make it, but I found later on had a discussion with Dr. Weber about this possibility. I do think this is the best choice for us. So, well, I will give you I will do a repeat talk here at the UFPB as well, which I did a couple of days ago, and I hope you will find something interesting or useful for your research. And also, I'm looking forward to any future possible collaboration with your university, with your group, and every professors. I think you already hear the introduction of myself. Just a very quick to recap. My name is Yunqing Xuan. I'm working in the Xuan University back in UK. I'm associate professor in civil engineering. Well, my research area is something I think very much similar to some of you here. You will see that later on in my presentation. I think that's all from my side about myself. Let's just as I start to share my presentation, see if it works, I suppose. Before I start, I think I have to say some of the slides I cannot show here. I noticed that it's going to be on YouTube because something is done by somebody else, my colleagues, without their permission. So I had to skip a few of slides, but essentially it should be okay. Right. Let me just start. Okay, I think I can finish around 40 minutes or so. During this time, please do feel free to ask me to stop. Any questions, I would like to hear from you. This is a bit weird for me because I really like the sort of interaction with audience when I give a talk. Somehow this remote thing may not be quite convenient for both of us. So do feel free if you have any questions, any problem, something you did not hear clearly. Just ask me to repeat or answer a question. Thank you. Otherwise, let me start. My topic today. Well, again, let's just repeat talk here. Is QPE and QPF, or quantitative precipitation estimation and forecast for flood research. I'm aware of most of you in the Department of Atmospherics, this sort of area, which of course is different from civil engineering, where I'm now in UFPB. So some of the idea you already learned that, so I won't be repeating this key idea. About myself, I will tell you why I do this QPE or QPF, weather radar, hydrology, all together. Why I do that, that was a long time ago. And then I will cover a little bit the introduction about precipitation estimation and forecast and the way how to do it. But of course, I imagine most of you have already learned that because you are from the meteorology department. And I will focus on radar-based QPE and nowcast. Something might be interesting to you. And also I will mention a little bit about the numerical weather prediction, which we had a couple of projects before. I will show you some of the results we have obtained so far, and especially in the context of flood forecasting research. And some of the further work and some ongoing projects, I also will talk about it. And afterwards, I think we have about 5 or 10 minutes discussion, or any question, please do feel free to ask any or to read any comments. Be more than welcome. Well, QPE, QPF, you probably already know that is quantitative precipitation estimation and quantitative precipitation forecast. The problem is here is you see we already have this weather forecast, nearly anywhere around the world, and you do receive weather forecasts, particularly precipitation or rainfall forecast every day. Even here in the UFPB, I can see the forecast on Sunday this week, it's gonna be rain. The problem is for hydrological use. I mean, for the downstream, the application, that quantity is really important. But unfortunately, until now, we still have been struggling with this sort of idea to get accurate rainfall forecasts about when and where and how much. Although in the last several decades, there has been a huge progress made so far. It get more and more accurate rainfall forecast, but still, as you can see later on, it's not enough. Therefore, it's still ongoing kind of research or improvement that you will see the relevance there. But for myself, I had my initial motivation. Initially I did my master and undergraduate study back in China many years ago, and then I followed up. I went to Beijing and worked there as the flood forecaster. It's a hydrological forecast center in Beijing under Ministry of Water Resources. So I've been working there for about 4 or 5 years. The main job duty was at that time is to monitor and make forecasts along very large rivers. I'm not sure whether you know the top 3 the rivers in the world, the number 1, number 2, number 3. But certainly in this country, in Brazil, Amazon is a big river, right? But in China, China is similar size. Also, it has a big river as well. So the first one is River Nile in Africa. I think most of you are aware of that. The second one, of course, here is Amazon. In comparison, this is the picture of Yangtze River, which is ranked as the third one. It's more or less the same length of Amazon River, but the river catchment size is smaller, kind of smaller, but compared with most of other river catchment in the world, it's still huge. So this is more than 180, 1.8 million square kilometers. That's huge. So what you see here, this blue one is the main river all the way from the upstream Tibetan Plateau, very high mountainous area. And you can see down here, to the, probably the video here is blocked your view somehow to the downstream of Shanghai, which is another mega city. So every flood season, my job at that time was try to make forecasts along this big river. The major flood season happens in May and June and July. At that time, a huge amount of river can come from upstream, as you can see the big area here, but also some major branch of the tributary from the north can bring in huge amount of water as well. And to the south, you see there's another river joining, and in the end, end up with huge river flow across this region. The problem does not stop there, and if you go further downstream, and hang on. Yeah, sorry, I have to close the door anyway. So let's resume a little bit. Yeah, hope everything okay. Let's continue. So this is a major problem. Major problem is it's a very long river, and then from Chongqing, where you see the Three Gorge Dam located here, and all the way down to another big city. So the traveling time of the flood wave can take about 1 or 2 weeks, and during this time, and you can imagine if you want to make a forecast somewhere in big city Wuhan here, you have really taken into account of all the water flowing from upstream. And not only that, the problem is during this period of time, there can be a huge amount of rainfall falling in this middle region. And if you don't know how much rainfall is, you're going to be in trouble. You can never make an accurate forecast. But this was my initial sort of motivation. I wanted to know how much rainfall exactly, so we can take into account that rainfall, and then we can translate that rainfall into river flow. Therefore, we make a very good forecast. So this is what why I started this topic back 15 or 17 years ago. So this is actually one of the use case in this sort of QPE or QPF in this river basin-wide flood forecasting. The major sort of objective here is trying to account for this rainfall forecast so that we can get accurate the flow forecast. This is for very large river basin. Same thing happened probably in Amazon and River Nile. We can also make use of this idea. But very interestingly, if you look at a very small area, so to say the urban area, the urban region, nowadays you see this sort of flash flooding, which can happen very quickly. This is another case study I did when I was doing my PhD back in the UK in Bristol in 2004. That's another famous sort of local flooding in Boscastle, which is a beautiful place in the southwest coast of the UK. What happened was on that particular day, the 16th of August 2004, just within 2 hours amount of time, and a huge amount of rainfall falling in that very, very small area. As a result, what you can see here already on the picture, well, this is actually someone took this photograph in a coffee shop. So you see the car floating around. So the problem for the hydrologist was it's unable to make any forecast, effective forecast at all, because it happens so quickly. By the time you know the rainfall falling on the ground, you probably won't be able to do anything to run your model to make forecasts. Therefore, in this particular case, you would have to have the rainfall forecast beforehand. Otherwise, it does not make any sense in terms of dealing with this urban flood forecasting. This is another extreme case, of course. So this shows the utility of using this rainfall forecast of QPE in the context of flood research. But currently, well, traditionally, I would say as a hydrologist, which is my background initially, we have rainfall observation from rain gauges. But nowadays, not only we have rain gauge, we have weather radar. As Dr. Weber just mentioned that you are trying to use S-band radar in NATO. So we have been using weather radar for some years already. So I can give a very quick recap about, you know, which one better, which one not so good in certain areas. We all know this rain gauge, how it works. It's a tipping bucket rain gauge. Basically, it is direct measurement. It's just depending on how much amount of water received in that funnel. You can get very accurate measurement of rainfall amount, of course, over a period of time. The problem for this rain gauge is it only measures the point of rainfall. We all know that we sometimes do need to have a kind of rainfall distribution, which cannot be given by this rain gauge measurement. Therefore, we have an alternative. The alternative is the weather radar. Fortunately, I can see the animation now here. You see, the weather radar is based upon this antenna, which can send off this electromagnetic wave, and then that wave will hit back by the raindrops, and the raindrops receive this kind of signal received by the this receiver in terms of energy. We call it reflectivity. So on the right hand side, you see this animation. I would say actually it's observed by the UK weather radar in 2006. They just showed an example of how useful weather radar can be in terms of giving the rainfall distribution. It's quite clearly here is not only the rainfall is shown as kind of intensity or amount, but also we can see its movement. This will be related to another topic of nowcast. So all of this radar observation, if you studied radar meteorology or radar hydrology before, you will know that based on radar equation or Marshall-Palmer equation, which links this energy reflected back by the raindrops, we call the reflectivity, with the number of raindrops over a particular amount of time. And that number of raindrops further associated with this R, which is rainfall rate. This is how radar works, weather radar works, or rainfall radar works. So it links energy to the rainfall rate or rainfall intensity in a way. But of course, here we have A and B, two constants need to be calibrated. Nevertheless, the weather radar can give you not only the amount of rainfall at anywhere, it also gives you the advantage of a quick scan. So in the UK, we have every 5 minutes get a radar picture around the whole of UK. Currently, there are 18 weather radars in operation in the UK. They are C-band radar, single polarization radar. I heard from you that you are trying to use S-band radar. The C-band, S-band, or further X-band is different wavelengths of that electromagnetic wave beam. So S-band is much longer than C-band, so it's C-band against X-band. It will be related to the capacity where how the resolution. So S-band basically have a larger or coarse resolution, but it can detect very far larger area. In contrast, C-band can get more accurate or more higher resolution, but correspondingly the distance it can detect, it gets shorter and shorter because of attenuation. So in the UK, we have, so to say, this spatial resolution at 5 kilometers in general. and 15 minutes. This is from UK Met Office. It's available, not public, but data sent to other applications, water companies and the environment agency. They all have the other sort of data which has much higher resolution, 1 kilometer in space and 5 minutes in time in condition coordinates. Well, of course, there have been some very serious data quality control. So this is supposed to be the better rainfall estimate so far in the United Kingdom. And this slide shows you how different this weather radar the image or observation can be from that observed by Raingauge. To the right-hand side, you see these are non-Raingauge from a small catchment somewhere to the south of London. You will see another case study later on. So to the left-hand side, let's see on the radar image distribution over the catchment called Medway. Normally, as hydrologists, if you do the rainfall analysis, you would have to use Pearson polygon. And sometimes nowadays you can use this interpolation, spatial interpolation. So you can have a sort of a distribution over the catchment. However, if you look at the two pictures closely, you see they are different. Although at some point they can be the same. You see clearly the advantage of weather radar here, it can give you a very detailed distribution, spatial distribution over the area. The problem is the quality of the QPE, so from weather radar, is not perfect. It's quality or accuracy. Basically, there are several major sources of error or noise which can interfere with weather radar data quality. One is the ground clutter. Basically, it's like they reflected back the wave from ground. And second one is bright band. If you studied the weather radar meteorology already, you know the bright band is kind of results from a melting layer. We'll see that later on. The third one for S-band is not big problem. This is called attenuation, because when the weather radar beam going through the rainfall field and reflect back, the signal or the strength will be weakened by or absorbed by the raindrops. So the smaller circular wavelength or the higher frequency, the higher attenuation. So this is why the C-band got a problem with the attenuation, and X-band is even worse, so to say. But after all these three, it still have problems called bias. The bias is always a problem. It can be as much as 50% compared with the Raingauge. The bias are always there. So you can see now the radar and the Raingauge. The radar give you a distribution, but not that accurate. On the other hand, the Raingauge give you a very accurate this gauge measurement, but not distribution. So how can we combine them together? That's another very interesting study area. This slide shows you one of the projects we did a few years back. This is one of the first so-called dual polarization radar we tested, I think in 2005, 2007. What you can see from this map, this is London. Not sure whether you can see my mouse cursor clearly. And down here to the south, we have many Raingauges. This is that small catchment, and the weather radar is just sitting somewhere here with a larger area. This is radar looks like, and this is its radius. So this is so-called a dual polarization radar. The advantage of this kind of radar is can have two different quantities of measurements because it has both horizontal and vertical polarization. I can tell you not only the rainfall, the amount or rainfall intensity, but also the type of rainfall, whether that is hailstone or snowflakes or just raindrops or ice crystals. In addition, it can also tell you the size and distribution of that drops. In a way, this is supposed to be better than the traditional single band radar. That was the one project we did back in early 2000. And we also use this we have these two VPR, the vertical pointing radar. It's now just next to my office, not far away there. We have the two. We use it to vertical pointing radar to do one important job. To look at this, see to the right-hand side, you see the vertical distribution. The horizontal axis is the time. The vertical is just height. You see how the variation at one single point vertically, that's the variation of this very strong, the bread band or melting snow layer. So if radar beam hit this layer, the result will be like a very strong signal. And you might be thinking, wow, that is strong rainfall, which in fact is not. So that's a big error here. This is something we need to remove. And in that project, we're trying to evaluate or appraisal, doing appraisal for this new weather radar based upon its hydrological use. So we have this radar and remove all the noises coupled with hydrological model and to see how this radar rainfall can be useful in driving a certain kind of model. We have distributed model, MACSHE, have a semi-distributed model, PDM, and we have a lumped hydrological model, PRTF as well. And we compare the radar rainfall with the rain gauges, and we have a single polarization radar and dual polarization radar at different time steps. This is one of the paper we published and see how, in general, this radar works well with its applications, but still it's not as we expected, a big jump in terms of quality. Just some kind of improvement in that region. And you can see here, it's driving several hydrological models downstream. They work reasonably well, I would say, compared with the rain gauges. So this already shows that even though the radar can contain huge amount of errors in some time, but still after this model calibration or validation, you'll see it's not that bad. Another technique regarding the estimation, called QPE, quantitative precipitation estimation, is trying to see how we can combine this multi-sensor. One is from rain gauges, the other one from radar, to see whether we can take advantage of both sources of data. On the one hand, we have distribution, on the other, we have point measurement, very accurate. The method that we have made use of the Kriging Interpolation, Bayesian updating, etc. Once again, this is another very interesting topic, and there are many papers published already. If you're interested, you can have a look. And this is also a very good idea. We call it fusion, sometimes fusion or merging of the two sources of data in order to provide QPE. And this is one way studies, one of my master student did to use this so-called Kriging interpolation, trying to merge this weather radar data with rain gauge data. Basically what it does is try to quantify so-called the coherent structure, the spatial variation, and then apply that structure onto the rain gauge data. Then after that, so we are supposed to get a mixed picture of both. The radar problem, this picture shows you the key problem, attenuation. This is 2015. There's a big flood in northwest part of the UK. The city called Carlisle, the beautiful city in northern England. Well, you can see that here you got a lot of mountain here, and this is big valley. And the somewhere the radar to the east coast, west coast of the next to the city. And the problem was for that particular day, the Met Office did not issue a proper warning. What happened was that the radar attenuation, because it's so heavy, somehow the signal wasn't strong enough to trigger a major warning. So that was a problem. So you see here, the attenuation is another big problem for weather radar. That can also be a very hot topic for study or research. So we also did a lot of research trying to correct the bias using statistical methods like quantile mapping and quantile regression. The problem for this sort of research, well, trying to address is it's not quite consistent. You see at some point you have 1-to-1 or one, this sort of relationship. The problem is you cannot apply that correcting a factor to the whole map, to the whole distribution. So that's the common problem. Therefore, you have to use the kind of statistical approach to remap or correct so-called bias to improve the weather radar quality. And this somehow we use it to correct the rainfall field to drive another model from Europe. It's called HAB model, it's hydrological model. The result, well, it's quite encouraging. I would say I cannot go into detail. Let's just show the one of the applications. Well, so far I have been talking about the estimation, but in fact, I think for hydrological use, if you can still recall, my original intention is trying to incorporate the rainfall forecast in the hydrological simulation. Therefore, we can effectively extend the lead time to gain further kind of 1 or 2 weeks lead time in that Yonge River flood forecasting case. So for the precipitation forecast, we already know that we can use the numerical weather prediction, and we can use so-called downscaling, use the land model, local area model to reach very high resolution. This is from numerical modeling side. On the other side is so-called radar rainfall forecast. The radar, because it generates a series very quick scan of distribution. As you have seen already from that example picture, this rainfall system can move along certain direction. Therefore, you can fairly make a good forecast with a very short period of time to extrapolate the trajectory of the rainfall system. And this technique called nowcast. Well, I won't cover too much here because you will learn this already. This is numerical weather prediction. So it's just kind of 3D, the description of airflow together with the energy equation, but on the spherical coordinate. It shows how it works. And we, again, back 10 years ago, I did this kind of downscaling. At that time, it was called MM5 from America. Now you have WRF model, you have many other models at different scale. The idea is the same, just trying to increase the resolution of this weather model to the downscaling. From an original global model, you can have 250 kilometers down to can be as high as 1 kilometer spatial resolution. This again is, we use that numerical weather prediction, trying to see how this sort of downscaling, this MM5, can help and other this WRF as well to see how they can produce, whether they can produce to the left down left corner. You see the distribution of weather radar, whether it can reproduce that picture or not. To the right hand side, this is kind of conventional global forecast from GFS from America. Apparently, you can't see anything apart from the fact that it's just a rainfall area, which you kind of melt rainfall. Because of the resolution, it cannot capture the local topography, etc. This was an experiment we did many years ago. We used numerical weather prediction coupled with a European weather forecast that produced a good ensemble forecast. One thing highlighted, two things highlighted here are, on the one hand, you see these are different ensemble members. They more or less can show that heavy rainfall can happen somewhere near the west coastal area in that region. However, none of that, those members was able to capture the exact location or amount. The location is supposed somewhere here, but they all somehow shifted to the northeast part. On the other hand, if you look at the right-hand side, that is big improvement. If you reduce the model grid size, therefore increase resolution, so you are able to reproduce very high mountain rainfall, can be as high as 100. This is also quite good and important. So for hydrological use, so one of the things I think we've been struggling with this numerical weather prediction or downscaling of this rainfall forecast is that from a meteorologist's point of view, they are all okay, more or less, somewhere near that region. But for hydrology use, because you're looking at a particular catchment, if the rainfall forecast outside catchment, it won't have any effect at all. So that causes problem. So how we can account for this kind of uncertainty, that's a challenging issue. And that is another study we did many years ago again, about 10 years ago, 2009. It's a downscaling coupled with a small area hydrological model, trying to see how this ensemble prediction can improve the capacity of model in terms of representing this uncertainty. What you can see here, initially, the model is underestimated a lot. Not only that, it cannot cover the real so-called river flow. After bad correction, after this post-processing, we were able to capture more like the distribution of the flow. So it's in that particular study, we had 52 member ensembles. So this is a way to try to quantify, account for this ensemble, this uncertainty from numerical weather prediction. And more recently, we went further to apply one of the most current, I would say, UK model called the UKV. We had a project with the UK Met Office back a few years, 5 years ago. So we tried to first make use of the 25 kilometer resolution global forecast, then going down all the way to from 12 kilometers run over Europe, and then 1.5 kilometers this resolution over the UK. And then we coupled that with our hydrological model or catchment model. We try to see how they work within for lead time about 1 day, 2 day, or 3 days, 1 week, etc., etc. And you can imagine, of course, if the longer lead time, the worse the quality or the higher the uncertainty. All of this is now running on the HPC platform, the huge clusters. It's mainly because, not because of the hydrological model. Normally you can run hydrological model on your desktop in the office. It's because of this huge, the weather model. So that is another project. And this is part of the result we have published by one of the postdocs back in 2015, using this platform to see how UKV can help in terms of producing a longer lead time. Again, somehow within 24 hours, 36 hours is still okay, but beyond that, you see a big drop of the forecast quality. Well, back to the point of nowcast and forecast, because we have a numerical prediction which can fairly produce within 1 week or so this fair amount or fairly well this forecast. This is one very, I would say, famous this chart showing the performance or index of rainfall forecast. One from NWP, numerical weather prediction, the other one from radar. So in the UK or many other countries, people trying to combine these two methods because numerical weather prediction, it contains larger error within a short period of time compared with the radar. But that's how the error band is stable, it's not growing, not fast. On the other hand, if you look at a numerical weather radar, it gives you a very, very small error with very short period of time, lead time around half an hour or so. But as time goes on, nowcast become useless. So therefore, people trying to combine them together. Again, it's called merging. In the UK, we have NIMROD system, which essentially combine a numerical weather prediction mixed with radar extrapolation. And this shows the normally how can nowcasting work. You look at the rain band, we call it rain band, and you can try to figure out the speed or velocity, how the rain band move to the next step. And then again, you can extrapolate. This is very intuitive, to be honest. However, it does not account for so-called growth and decay problem because rainfall system can grow, get stronger, or can get weaker, and can even disappear, or can even rotating around. So that's not that easy. And again, the nowcasting here is very hot topic, and many people just trying to produce the good quality of nowcast, different algorithms. This is very simple, just showing how that idea works. We have weather radar to the left-hand side. We have numerical weather prediction, which produces, very similar. They can results with still some difference. So that sort of nowcast plus it forecast and merging is trying to combine them together. Now, you can think about it, this can be done very easily using weighted average, for example. But the problem is they are not going to be physically consistent. So therefore, we have nowadays have another forecasting system back in the UK, we call it STEPS, which kind of stochastic rainfall ensemble forecast system. The beauty of this system is originally developed by Alan Seat, one of our friends back in Australia, trying to decompose the rainfall field into smaller scales and propagating that different scales of system with different velocity, and then put them back together to account for the uncertainty. This is one example showing how the steps works from several members. Actually, there are, I think, 24, 23 members of the rainfall ensemble at any single moment in the UK. So you see they can produce similar but different, the nowcast. Yeah, this is UK steps rainfall nowcast. It's still being used as a standard system in the UK. And the job, the work we have done so far, we trying to see how steps can work with hydrological model. What we have found, within 60-minute lead time, such a system can give fairly good results compared with one single deterministic forecast. So the added value here is the uncertainty represented in that propagation of different rainfall systems. But of course, overall is the big challenge here, the quality of radar data. Sometimes after so many vigorous correction methods being applied, you can still see, for example, this is one of our case study here, in the middle of the catchment, you have a bright band, so to say. Somehow it is there, and they give you overestimate of flow. We couldn't understand what happened because you check the Raingauge, we can't see that, but it does happen over time. So that's, again, that's a big problem. The other problem for this of the study is we don't have ground truth. That means although you have very accurate measurements of Raingauge at certain location, you don't have accurate distribution. You do see the distribution at a picture from weather radar images, but the accuracy is not good, so to say. So again, this is another study area. People look at how they can improve the quality of weather radar, this estimation, as well as nowcast accuracy. But of course, back to the numerical weather prediction, the problem we have seen so far in the context of hydrological use is uncertainty. Since you have studied meteorology, if you think about the numerical weather model, basically it's just discretize this continuity, the equation into a small grid size. The problem is, depending on how fine your grid resolution is, you may not be able to capture these fine waves. Therefore, you are losing capacity of representing certain physical or dynamics. This is one thing. The second one is, even with very small grid size, we call it subgrid process, like if you have a convective cloud, which can happen within 1 kilometer, but if you don't have that high resolution model, it cannot represent this called subgrid process or physical processes. You need to do the parameterization that give you further uncertainty. The last one is so-called nonlinearity, due to this called the butterfly wing impact or chaotic problem, because even very small initial condition disturbance can cause totally useless of your model simulation. So this has been observed. Therefore, as hydrologists, if we look at the result from numerical weather prediction, most of the time for longer lead time, the result is not quite impressive. So sometimes we cause trouble. Well, although we have this problem, that problem, you know, but things had been improving over the years. First of all, the numerical weather resolution, weather prediction resolution kept going up and up and up, and performance being improved over the years. So, for example, in the UK, you have 1 kilometer resolution simulation over certain areas, and the result is quite good now. And the other thing is recent advances in the climate model simulation. This is another of my study area. I can see that we cannot even simulate climate over 100 years using this high resolution like 1 kilometer. This is a big achievement. On the radar side, we now have the mobile, community-oriented, very high resolution weather radar available, so-called X-band radar, particularly useful for urban flood warning application. I will be showing you shortly after this slide. And some other like ensemble forecast, interpretation, data simulation, model coupling, uncertainty representation, and multi-sensor merging. I just give you a sense about this kind of forefront of all of these related studies. You might be interested to pick up one of them. I'm sure that they could be very, very interesting. The recent advance in radar technology is a so-called phased array radar. Traditionally, if you look at your S-band radar, it's going to be huge. It has a huge antenna, and it has to be mechanically rotating around in order to have a scan over a large area, not only horizontally. Sometimes they can be vertical like this, tilted. And the most recent advance in radar technology is so-called flat panel radar, where this kind of scan is based on electronic scan, changing of different phase. They can have, you can see that's different small pieces of component. This is another project I'm currently leading together with some Chinese partners and UK partners as well. We looking at how to use this advanced weather radar to help build early warning system for big cities in China in dealing with urban flooding problem. So this advanced phased array radar is small size, something like 1 by 2 meters square. So you can see from this picture, this is already being used somewhere in Guangzhou with made by one of the partner, Narita, there. And from Guangzhou City is next to Hong Kong. So Hong Kong somewhere down below here. So this is probably one of the richest area in China. So they invested a lot in terms of doing, fighting against urban flooding, because huge losses can be caused by urban flooding. And they now have the 1, 2, 3, 4, 5, I think 5, this sort of radar available to cover this area. The beauty of this new device is high resolution. If you want to do a very accurate urban flooding simulation, one of the things, of course, you need to look into hydrodynamics. You have all sorts of model. Now it can be very useful. I have seen that other partners, they are model simulating this surface flow with the resolution as a few hundred meters or even tens of meters. But on the other hand, they don't have this accurate rainfall distribution. So this is where we can use this X-band with very high resolution. For this particular radar, it can be 60 meters, and it can also give you very quick scan. In this particular case, operationally, they can provide radar image every 90 seconds. That means 1.5 minutes. The main idea of this project is we look at a small area, we try to model this urban drainage network, and by couple that urban model, the flood modeling with weather radar with this small area, we try to account for this urban flooding. So whenever we have this, the high accurate rainfall input, we can run the model to give a prediction over that particular area. But of course, this idea can be used anywhere in the world. In line, you have the model set up there. Once again, for this sort of project, the big problem was the data. So we spent a lot of time just trying to collect data to build a model. This is how it look like, how complicated even for that very small area, what kind of data are needed, the pipe flow, etc. This new radar, well, just focus on the radar itself. The new radar is got dual polarization, horizontal polarization, and vertical polarization. Had all sorts of advantages as I mentioned already. So give you not only the type, not only the amount, but also the type and distribution, and also benefit from the electronic scan. It can give you in the next slide, I think you will see how different. On the left-hand side, you see a S-band radar, which is somehow similar to the radar you have in NATO. And right-hand side, the similar event, the same event, but observed by that high-resolution radar, urban radar. But you can see, well, you probably cannot see it clearly because of the video conference setting. But on my screen, or if you have watched a PPT, you see a quite refined structure available in this right-hand side. Not only the the radar, the phase array radar give you less amount of noise. You see that many background noise there in S-band radar. The other very useful feature is it can give you a very quick 3D representation of a certain rainfall event. This is one of the examples shows you. To the right hand side, you see that rainfall structure, vertical structure propagating horizontally from east to west as time goes on. So not only you have horizontal scan, you see the distribution over large area, but also you can cut through certain place to see the fine structure vertically. And also keep in mind, it's called Doppler radar. Although that wind speed sometimes might not be so useful for hydrological use, it does give you idea, especially in a storm case like typhoon or hurricane. It gives you a observation of wind speed distribution, again in 3D sense. This might be interesting to you because this shows you actually by combining several radar together, we could remove effectively all the noises on the background of S-band radar showing to the left-hand side. See that the signal is just completely buried by this noise. But on the other hand, if you look at this X-band radar, it's very clear this noise has been removed. This another case to show how quickly it can respond with to the so-called meso and macro scale system. Again, this system is just a few kilometers away, and you see a very small size. However, it was captured by the radar. This is very nice because for urban flooding, sometimes you just, from Raingauge especially, you just can't see this kind of small system happening over one area. So this gives us the advantage of capturing this big event. This is another case of noise reduction. Once again, it shows advantage against S-band radar. One thing I can say, well, not always like the S-band is not that bad. S-band can be very, very useful. Let's just particular case in Guangzhou because it's a local topography, so that they have such a big problem. Okay, I don't think that will happen in Nepal or any other place, but this just shows a very particular example. It doesn't mean that S-band is bad. In fact, it's very, very useful, very large area, and a very small attenuation as well. This is wind speed, or right. This is give you an idea how we can receive two different quantities from the vertical and horizontal scan. To the reflectivity, it can make a difference between the raindrop as well as their types. So this is some additional information we can have. And also by take advantage of that two different measurements, if you look at the left-hand side, there's the called by block by the building, high-rise building. To the left-hand side, you see this just empty area. Somehow, it can be compensated by using that particular algorithm to the right-hand side. It's a kind of advantage of this small radar. But of course, in terms of hydrological yield of flood forecasting, flood warning, the fast response is essential. This showed an example just, I think, a few hours. You can see how fast this system and flooding can be caught by this heavy rainfall system, scan from that region. Without using this radar, we wouldn't be able to capture this event, not alone, let alone do a forecasting. So this is show the advantage of using weather radar to monitor to the early warning system. This is another case showing the wind speed as well. Okay, yeah. So this is super cell, this storm happened in 2019, earlier this year. They're very heavy moving along to the south from southwest. I think that's nearly all from my side, talking about the weather radar, talking about numerical weather prediction, how the QPF, QPE can be useful in doing the hydrological research, particularly for flood simulation, flood forecasting, and flood risk management. I also showed you, the advantage or disadvantage or any problem within certain techniques or technologies. Still there, but I would say this is a very active area of research. So this slide shows you next year I'm co-organizing an event in Nanjing, China. So we have internationally have a very active community for those who've been actively using the weather radar in hydrology. So this is 11th International Symposium on Weather Radar and Hydrology, which will be happening next year. So if you have any interesting study to be shared with other researchers, you're more than welcome to have a look, check it out, this website, submit your study, and I would be very happy to see any of you can come to Nanjing next year. But of course, we have many other opportunities in future, if you like. And finally, I would like to thank my sponsors. So my trip here down to UFPB is supported by Newton Fund in the UK, together with CONFAB on the so-called Newton Fund UK Academy program. And yeah, thanks to UFPB providing this afternoon this space. Otherwise, I wouldn't be able to make it. And thanks to you all for your patience listening, and any questions. Thank you.
Thank you, Dr. Xuan. I'm gonna open for questions here, right?
Yeah, in my contact detail, if you wish to make contact with me.
All right. Okay, okay. Questions? Se você tiver alguma pergunta e não quiserem fazer em inglês, pode fazer em português que a gente vai traduzir. Tá? Aí a gente pode traduzir e passar aqui para ele. Se quiser fazer em inglês, aí tem que vir aqui para frente. O microfone vai até você. Tá bom? Pode fazer em português que ele traduz.
Sorry, I can't hear that clearly. If you can just repeat that question.
I'm just asking them if they have questions, and if they want to speak English, I can translate for them.
Yeah, yeah, of course.
Okay. Alguém? Mais alguém? I have a question.
Yeah.
You talked about some problems that we have when we are trying to have a quantitative precipitation from radar, right?
Yeah.
And you talk about bias cluttering,
Yeah.
brightness band attenuation, right? And
Yeah.
I mean, depending on the kind of precipitation, we have different ZR relationships. And you mentioned the Marshall-Palmer relationship.
Yeah.
When you use a radar for some specific case, you always choose Marshall-Palmer ZR relationship, or you try to make your own ZR relationship to use on your study case, for example.
That is a very good question. Actually, the Marshall-Palmer equation is all sorts of uncertainty, because when you try to quantify that equation in terms of two constants, the problem is, well, the fact is so every event you may have a different numbers for that A and B. So what we normally do, I mean, from a math office viewpoint, they do the so-called calibration, because we cannot just every time when you use data, we just calibrate. So somehow they have to run the calibration process, in which, you know, study areas, catchment, for example, equipped with very dense Raingauge network and with very accurate rainfall measurement. And then that place will be observed by both radar and the rain gauges. And then they can link together to calibrate. And you can see, I think you can imagine that for every single event, you probably will end up with different numbers. But overall, I think they have to produce a set of constant, a set of parameters that can be applied to all the other events. And this work can be done every few years. And this is exactly what has been doing in my office, or probably similarly here in Brazil as well. But I think the other countries I have seen so far, sometimes they just don't want to do that. They can provide you directly with so-called reflectivity, that is that. And that will be up to you to make calibration. So you need to really compare that with your rainfall measurement. That'll be your job to do that. But again, you have to be very careful, because so every time, even different cloud, different precipitation system, you end up with different numbers of that parameter. This is because if you look into that equation, the rainfall, raindrop distribution, which at the end we assume, and the size distribution will not be the same. That's for sure. So that's just a matter of how different they are in terms of finally get different A and B. So this so calibration problem. This is also shows you that why we have a bias. There are some other problems, like you can have overshooting problem, where the radar beam is just simply too high and the rainfall happens below your radar beam. Therefore, you radar just blind. You can't see what really happened. So that's also a problem if you can't have that 3D structure. But back to the application, we have all sorts of problems. However, what we have seen so far, as well as in many other related researchers, such a coupled model like weather radar data plus the hydrological yield, not that bad. And most of the time you can get a reasonable wild simulation. So out of this combination. But once again, you have to be very careful with huge bias. Sometimes you have this bright band, sometimes you have this noise. In that particular case, you have to pay attention. But overall, I think radar can do a good job. And taking into account of its advantage, like give you early warning signals and rainfall distribution and nowcast, I think that's is a reasonable argument to say that we can still carry on the use of weather radar.
Okay.
Yeah.
Yeah.
Bias, talvez.
Okay.
Para falar aqui um pouco. Se falar meio mal, me corrija, tá? Hi.
Hello. Yeah.
There are a lot of methods to remove the bias of the quantitative precipitation. And what methods you have the best results about of the remove bias of the quantitative of precipitation?
Yeah. Okay. There are a lot of publications around. I think you can check it out about the bias correction, etc., etc. So that really depends on that will case by case. Sometimes your one method can work in this region, may not be able to reproduce a similar result in other region. But on the other hand, you can think about depending on how much complexity you allow for, you can have a very straightforward like regression, right? And this is exactly what the meteorological surveys do. They just do the regression. It's very simple, but of course you can argue this not good idea. So the very rough idea that for hydrological use, you can have a catchment, you can get a catchment rainfall, and then compare this catchment rainfall with what you produce using Raingauge. There certainly will be a bias, and then you can just simply apply that factor, 1.2 or 0.9, etc., and then to apply that factor onto each and every radar cell. But by doing so, of course, you're ignoring the fact that the error can be different, will be different, of course, from each cell, from this cell to that cell. But this is how it works. On the other hand, you can also have a more complex configuration. Like nowadays, we can have this Kriging method with so-called eternal drift. It's another commonly used method, the Kriging Interpolation with external drift. Basically, what it means here that we'll try to use Raingauge to interpolate to get a field, right? To get a field, or you can think about it when you try to apply that the radar rainfall information, every point over catchment, you are doing a Kriging interpolation. And you already have information measured at Raingauges. That measurement of information using Raingauge data is called drift or external forcing factor. Try to affect the overall interpolation process. So that's a Kriging method with external drifting. And some other colleagues, they trying to use ensemble method, play with all sorts of parameters like that radar equation to account for the so-called uncertainty, because we already know that we can't have just one single radar equation with one set of A and B. That's impossible. So you may have different measurements over the years, and then you try to quantify the uncertainty in that parameter. And therefore, you can produce not only one field, one image, you can have many images as well. In a way, you are making or ensemble estimation. This is another way forward. But doing so, of course, you will be involved. You have to be responsible for the explanation of this to your end users, because people just simply confused. They which one should I believe, and which one is better, etc., etc. But you know that you just simply don't know which one is better. It's uncertain. So that way, try to quantify this uncertainty or errors. But I think, yeah, you can have options from very simple linear regression to a more complicated case, like this the Kriging method. And more recently, people use AI, artificial intelligence, try to train their data set, right? Try to fit different structures. So like neural network, etc. That can be done as well. So, but basically, I would say that belongs to a certain statistical method domain. You can have many choices as well. This is my understanding.
So, Dr. Xuan, I'd like to thank you again. I think our students are a little shy here.
All right, don't worry.
For sure, we are gonna send you an email soon to talk about a lot of stuff that we want to do together with you. As I told you, we have an S-band radar that is available for us since last year, I guess, and we have like 5 of this data to work with. and doing some simulations. It's going to be awesome, right? So I'd like to thank you again, and I think you're going to fly back tomorrow, so have a nice flight, and thank you a lot.
Okay. Okay. Thank you very much. It's really my pleasure to talk to you guys, and I'm really looking forward to receive any feedback from you. And of course, if you have any questions, do feel free to send me email, follow my Twitter account, and if anything we can collaborate, for example, to share certain experience, I'll be more than happy to do that. Thank you again. Thank you very much.
Okay, thank you. Bye-bye.
Bye.
Desligou agora, né?